What does this drill bit, pasta, and spring all have in common?
They all share a property called metachirality, but what does that mean? Let's figure out what normal chirality is first. You may be familiar with the old video game Tetris. In Tetris, it's really easy to play with the light blue, yellow, and purple pieces because you can easily visualize which orientations will work. However, it's harder to play with the dark blue, orange, green, and red blocks because they are mirror images of each other. If you hold up a green block to the mirror like an S, the mirror image is like a Z. You can't get the Z shape by rotating the green piece in a 2D plane. Same goes for the dark blue and orange pieces. The mirror image of the original piece is different from that piece. That's what chiral means. These pieces are classified as chiral. Blue and orange would be a chiral pair, and so would green and red. If chiral means not the same as this mirror image, then achiral would mean it is the same as this mirror image. If you hold the purple T block up to a mirror like this, then you can easily get the mirror image by rotating the original figure by 180 degrees in a 2D plane. Same goes for the light blue and yellow blocks. These three pieces are achiral pieces. The pasta, spring, and drill bit from the beginning of the video are all chiral objects. The lips on the drill bit are slanted rightwards, but the lips in the reflection are slanted leftwards. Since the mirror image is different from the original piece, the drill bit is chiral, just like the pasta and spring. What happens to the reflection when I rotate the original piece in a certain direction? The mirror image of this blue J block is an L, as long as its color doesn't matter. If I rotate the J 60 degrees clockwise, then the reflected L block has to turn 60 degrees counterclockwise. This works for everything. To understand metachirality, we'll need to know the different kinds of symmetries. There's rotational, translational, and reflectional symmetry. These are also types of transformations, but we only need to know the symmetry aspect. If you combine a translation and a reflection, you get a glide reflection, which you may recognize from math class. However, if I combine a translation and a rotation, I get a normal rotation. Wait, this works for anywhere on the plane, but what if I translate it up instead? I'm going to take this J piece and do a glide rotation, but instead of translating on a 2D plane first and then rotating it, I'm going to bring it up into the third dimension, and then rotate it 60 degrees to the right. Here, on this stick I continued this, and it's a new kind of symmetry, screw symmetry. Would this J tower be a chiral object? Well, since it looks like the pasta, drill bit, and spring, I think so, but let's test it. Here, I built a chiral pair of the blue J block using the orange L blocks. Color doesn't matter. With the J tower, I translated up 3 centimeters and then rotated the figure 60 degrees to the right. But for the chiral pair, the L tower, I translated up 3 centimeters like before and then rotated 60 degrees to the left. So since this J tower isn't the same as this mirror image, it's chiral. And since you can't get the mirror image by performing the same set of transformations, it's metachiral.
Pasta, drill bit, and spring are all metachiral objects because, like the spring, the reflection rotates in a different direction than the original object.
Thanks for watching!